All right, everybody who's feeling comfortable, you have no mobility issues, I want you all to squat. Okay, ready? Arms up. Legs parallel, knees bend. Keep your back upright and down. Yeah, and up. Okay, one more. Down. Up. Good work. We are multidisciplinary. So, my name is Kyle Kingsbury. You might know me as A for Online. Some people call me Jepsen Networks. I work at Factual by day, where I'm responsible for the care and feeding of distributed systems, but by night I do this thing called Jepsen. This talk is called Jepsen 2, Linearizable Boogaloo. It is in fact not the second, not the third, but the fourth talk in the Jepsen series, which should tell you something about consistency. Jepsen is not a benchmark. We're not interested in happy case performance or throughput. We want to know what happens when distributed systems are really stressed out. So we cut them in half, and we have all these clients make requests and keep a log about what happens, and then we measure that log and try to analyze it to understand what occurred. Now you're asking me, who are you and why do I care? Well, that's always a good question to ask. The answer is, my lord, that the net is dark and full of terrors. The problem with distributed systems is that they're allowed, at least in asynchronous networks, to delay, to drop, to duplicate, or to reorder packets. And the delays and drops, you can't tell the difference. Think about your friend sending you a letter. If you don't get it, did your friend ever send it in the first place? Or is it just being a little bit slow in transit? You can't tell. This is called a network partition. Partitions can arise because of garbage collection pauses, because of spanning tree or loop issues, network maintenance, seg faults and crashes in your local processes can cause delay in delivery. Faulty NICs. Broadcom is notorious for dropping packets in but not out, or a switch that issued flow control denial of service attacks against other switches when it was asked to slow down. Bridge loops, spanning tree. If your network is hosted by somebody else, you are going to have all kinds of pain, especially in EC2, where things tend to partition on a monthly basis. In the face of these failures, we want to do the right thing, to be intuitively correct. But what does it really mean to be right? Well, this is a simple program. Let's pretend that I'm going to walk through, like a basic sort of basic program or a C program. So I'll start over here. I've got a single variable called x, and I'm going to store the value a. So x equals a. And then I'll print x. That's a read. So I read the value a. I read a. I write b. Read b. Write c. Write d. Read d. Every read sees the value from the previous write. Things proceed in a single-threaded fashion. But our programs aren't single-threaded, they're concurrent. So the top process could be doing a write and the bottom process could read it. And then if the bottom process writes, the top process could read it. And so the top process might write the value a and later read b, a value it didn't write. But this is still understandable in a way because everything proceeds in this nice linear fashion. There's only one value for the variable. But it gets a little more complicated. Because when you store something in memory, that's 11 whole centimeters away. You have to talk on this wire and wait nanoseconds for it to get there. That's impossibly slow, right? So I invoke a message, and then I've got to wait, and it hits the source of truth, and it comes back and hits B, and now I've got the value of my read. So distributed systems have this synchronization delay, and that implies that the order of events in the system is ambiguous. By ambiguous, I mean weird stuff can happen. Let's say the value is a and I start a read. But then somebody else sneaks in and writes a value after my read started. They change it to b, and I arrive just a moment later. So now I've read this value that was written sort of after I started. Or I could have seen a if my read got there first. So the order is ambiguous. And the classes of allowed orderings, that's a consistency model. So the set of all possible interleavings in the system, that's a consistency or a way of talking about the safety of your system. But it's not that the orderings are infinitely ambiguous. You can't send a message back in time. So these lines can never go backwards. They always have to go the fastest you can hit theirs instantly, and the latest you could get your response is right before the response arrives. So there's this window of time between the invocation and the completion of an operation that defines the series of states it could interact with. That means that two operations that interleave or overlap with their invocation and completion ranges, they're said to be concurrent. This is a much better definition of concurrency than callbacks or sort of out of flow control order. What you're really interested in is between the time when you started the operation and when you stopped it, did it overlap with somebody else's operation? If it did, you could see either order. But Once the write has completed, we're guaranteed that any future read cannot possibly see the previous value. So that read is guaranteed to see B. And this guarantee in real time means no stale reads. We can do safe state mutation. We mean that everybody sees the same series of events and they have some time guarantees. So they could pass external coordination channels and say, oh yeah, I guarantee that if you do a read, you're going to see this next value. That time guarantee is powerful. This is sort of the gold standard for distributed consensus or for consistency. It's called linearizability. Now, linearizability is not the only constraint. We could relax it somewhat. We could get sequential consistency. And in this case, everybody agrees on what things happened and in what order they occurred, but not on when they happened in time. So it's kind of like letting those lines skew. If you hand off your request to a work queue or to a cache, you might have some readers see delayed state. So think about changing your name on Twitter, which I do all the time. Your name, Twitter says, yeah, your name has changed, but then other people are seeing the old profile for like a day afterwards, and it's because there's all these caches and things in the way, and so they're seeing sort of backwards in time to a previous state. But they always see old name then new name, not new name then old name, at least if the caches are behaving correctly. If the caches are not coordinated, you get this thing called serializability, and that's where the lines can cross. Everybody agrees that stuff happened, but nobody has to agree on the order. So a trivially serializable register for a variable could be dev null. You just do all of your writes to time like 10 and all of your reads at time 0 when the value is null, and boom, like that's serializable. Totally okay, right? And you're thinking, hey, wait a minute, isn't like acid isolation, isn't the strongest level supposed to be serializable? Like that's kind of weak, right? But it's not that weak because acid transactions can be really complicated. You could do something like change the value of x to be y plus 1 if and only if z is equal to y minus 2. All these constraints, right? And then the database has to figure out a time when that would be valid to apply. So it's actually a rather strong constraint. Now, time to talk about the CAP theorem. My favorite acronym, MRBBK, now MRBDC, says that acronyms are easy to make shit up about. And I'm going to make up some shit now. CAP says that if consistency, availability, and partition tolerance, you can get 2 out of 3. But a lot of people don't know that CAP-C is very specific. I mean, this is a theorem, right? If you have like disproved or beaten CAP, you have a paper to publish because you've messed up some math. CAP-C says that, I mean, you can prove things. This is real, right? CAP-C says that consistency is linearizability. No more, no less. Not sequential consistency, linearizability. And CAP availability is very specific. Every single request to a non-failing node must succeed. And P, partition tolerance, mandatory. Why? Well, if you give up partition tolerance and a partition occurs, your system will suddenly fail to be either C or A, and usually in spectacular fashion. So I assert that anybody who says they built a CA system just doesn't understand what the CAP theorem means. Now, this means we can have an AP system, which would be totally available, or a CP system, or something weaker, but you can't do all three. You say, hold on, right? I can work around this because you said that consistency models are the classes of allowed operations. So I could have like linearizability plus I'm allowed to read X at any time I like, or serializability plus like any reads of Y can be stale. But those are all valid models, and you can find infinitely many. So surely some of those could be CAP available. Well, Peter Bayless has put together a terrific map of these. So all this stuff up here in red, all of that. That is not available, at least not in the CAP sense. So the CAP theorem excludes linearizability, but another theorem excludes sequential consistency. And we have other theorems that say you can't have repeatable read, snapshot isolation, cursor stability, or serializability, and still be totally available. Now, you can be sticky available if you have causal or PRAM or read your writes. Those are OK as long as you only talk to a single node and you sort of stick with it. And you can be totally available for monotonic reads, monotonic writes, read committed, monatomic atomic view, and some others. So there's a continuum, right? The weaker consistency models, they're more available in the face of failure. But they're also harder to reason about because they let more stuff happen. And when I say weak, this is not a total ordering, right? It just means that more behaviors are allowable. Finally, those weaker consistency models are also faster. They require less coordination. Modern CPUs look nothing like a linearizable register, right? You do a read and like you get some ancient value from the past. It's been reordered with respect to other operations. If you want linearizability, you have to like erect a memory fence and you talk to the QPI bus and get all the other cores to agree that you own the register now. Finally, I want to emphasize that these weak models are not necessarily unsafe, right? Safe is determined in terms of the consistency model. So a CRDT might have like multiple points of state. Instead of a straight line, it could have like kind of branching forking structure. But that could still be safe. All of your operations could be preserved and you converge on some final state. So last year, we talked about NuoDB, Kafka, Cassandra, and Zookeeper. This year, we're going to talk about some new systems. People asked me to discuss etcd, and I couldn't find any problems initially. Well, the reason that is because Jepsen analyzed systems by adding elements to a set. So we would add, via compare and set, the element 0 to the empty set, and then we change like the set of 0 to the set of 0 and 1, and the set of 0 and 1 to the set of 0, 1, and 2. So you do all of these cas operations, and you do a final read. But in between the cases and the read, anything could happen, right? Like the database could say, oh yeah, I'm just going to journal all this stuff, and you can't read it yet, and then it could sneak in at the last minute and fix everything up. So we need to look a little closer. Jepsen now handles the database automation, the testing, the installation. It generates a history of operations against the cluster. It does generative testing. It makes up stuff to do instead of having this fixed schedule. And then it generates a history, and we check that with a tool called Knossos, which verifies the history is linearizable. Now, in order to check that a history is linearizable, we need to define like what the heck it is that we're linearizing. So we need a model. Right? I said that the state is linear. It proceeds in this nice order, right? So there's only one state at any given time. So we could model the system's correctness by having a function of the current state that takes an operation and returns a new state. And then we just reduce that function over all the operations, and you get a final state. If at any point something goes wrong, like let's say I write 1, read 1, or write 2, and then read 1, I can't read the value 1 from a register that has 2, so I'd return inconsistent. This means that I can verify any single-threaded history. Problem solved. Except that we don't have a single-threaded history. We have a multi-threaded history. So all these different clients are executing requests. They're making invocations and they're recording their completions all at the same time. And then we're trying to figure out what path through these operations could actually have made sense. What path is equivalent to a single-threaded sort of linear version of the state. And of course, if a process crashes, like this one here, 5 has died, we don't know if its operation succeeded or not. And so it could complete at any future time. You have to hold on to it. It's contemporary with every other request. So you can think about this like playing hopscotch. You take your history and you kind of try to jump, always moving forward between all of the different operations. And if you ever fall off the edge, or if you hit a path that's inconsistent according to the model, you know you've failed. So one way to interpret this history is like write 1, read 1, write 2, read 2. That's safe. But we could also read it as like read 1, read 2, write 2, and that's obviously unsafe. So we exclude those unsafe histories, and if we ever run out of possible world lines, we know we found a problem. The system is not linearizable. Now, the computational complexity of this is combinatoric. And we have a special way to pronounce this annotation. But all is not lost, right? We can apply heuristics. So we use degeneracy, we parallelize, we memoize, we have all these strategies. When I say degeneracy, I mean that the past is a fiction, time is a flat circle. The model only depends on the current state in the future. It knows nothing about how it got there. So if you find 2 equivalent states and 2 sets of future operations, they're going to linearize to the same final state. You don't even need to care about how they got there. You just throw it away. Just compact everything into one. And that degeneracy makes our state space much smaller. The other thing you can exploit is parallelism. So if you get a write, you've got 2 choices. Either it happens or it doesn't happen. And if the write completes, the path where it didn't happen gets pruned because obviously the write occurred. If you get 2 concurrent writes, it forks. You could have neither write number 1, write number 2, or 1 then 2, or 2 then 1, and now you've got this sort of combinatorial explosion. But every one of those states can be explored at the same time. All we have to do is model the state as a sort of pure object, the sort of pure world line histories, and then we have a function that takes that world line and forks it. And those forks can be explored in a sort of branching fashion. We could do a breadth-first search, but then we have the combinatorial explosion early. Or we could try to find shortcuts. So we memoize, and when we do lazy evaluation, we actually wait to evaluate the hard paths and try to find shortcuts around them. And then we can memoize it. So like imagine you're exploring a maze with a bunch of friends, and all of you have some paint, and you paint in the path as you go. If you ever come to a fork in the maze and you find that your friend has already painted it in, you don't have to explore, because you know your friend's going to take care of it. So this means that we can drastically reduce the amount of exploration that has to happen. Again, this connection between paths, that happens because of the degeneracy. If we ever detect that a current state is degenerately equivalent to some other state, we know we don't have to check it. Now, all of this should remind you of the word monads, and I'm not going to use that anymore because we're not hacker people right here, right? We're all like Lispers and not Haskellists at all. At least I'm not. But this technique, right? It's all parallel safe. It's very functional. We work with these mutable data structures, and the interesting thing is we've sort of modeled the execution of the system as this data structure that can be followed as a pure function instead of trying to actually evaluate everything independently. This technique of exploring the state space this way is adapted from Margot Seltzer's talk at Recon, where she talked about automatically parallelizing x86 programs. Now, those of you in the audience who are Haskellers are probably thinking, man, it's looking mighty attractive right now. Let me whip up some GHC. But I'm actually not that much of a Haskell wizard. I am more of a Clojure Sith Lord. So in true Emperor Zahn fashion, I'll pull out my shared data structures. So I can share state between my maps and vectors, and that means when I fork the world, I don't have to go and copy everything. I can actually keep most of the state in the same memory locations, and that allows me to have millions of versions of the world in a single process. And then we just throw a PMAP on it. It's not quite that simple, sadly. PMAP helps, but you start backing up because you're stuck trying to evaluate all those branches. We wanted to memoize and skip ahead and do all this nonlinear execution. And that nonlinearity means that we start pulling in some mutable state from the JVM. So CliffClick's concurrent high-scale lib has a hash map that's really good for parallel access. We've got the striped wrapper for Java util concurrent priority queue, which turns out to degrade terribly under load. Java util concurrent atomics for boxed cas state, and of course Clojure has great primitives for atoms, futures, refs, and so on. So at this point, I've got this program, but it's really slow. That n factorial thing is hard to work around. And my friend John Moore over at Comcast says, hey, we've got this cool thing called Tech Fund for doing research grants, and we really like it if you could, go build something bigger with Jepsen. So I did what anybody would do if presented an unlimited grant from the intergalactic space empire. I really thank you guys so much. I built a giant moon laser. So my moon laser is a 48-core Xeon. And this is Knossos consuming 97% of all 48 cores. So yeah, functional programming, it works. In the back of the room, I know there's 8 Haskell people we could do it faster! And so at this point, very proud of the technological terror I've created. The tiny Moff Tarkin in my head says, you prefer another target, a military target, then name the distributed system. Dantooine. No, RabbitMQ. They're on RabbitMQ. Very well. We'll deal with your friends there. So, RabbitMQ is a message queue. It speaks a large portion of the AMQP spec. It's got all sorts of really cool features. It's not only a distributed queue, but it's a message broker, and it's got pub/sub and point-to-point, and all these really cool features. And with those really cool features, you could do stuff like turn it into a lock system. You can turn it into a lock system, and this blog post tells you how. So you take a queue with a single element in it, and you get an element from the queue, and while you hold it, you hold the lock. That's that black bar up top. And you release your lock, and somebody else can go and pick it up. And the limit, linearizability guarantees that if somebody else does a concurrent get on that queue, they're not going to be able to claim anything until I return it. So these black bars will never overlap because those lines always go forward. This is why linearizability is really important for mutex. But it's not quite linearizable, really, because if a process crashes, it needs to reclaim it. And so it gets a little complicated, right? The Rabbit docs are actually pretty clear that partitions are sort of a problem, especially for Amnesia, the underlying distributed database. So you'll see these errors like inconsistent database, running partition network. What does this even mean? Well, it means that ribbing on Erlang messages, man, it's so easy. It's almost as bad as Clojure stack traces. So, so you've got 2 nodes that are 2 RabbitMQ servers that both have a copy, but they're in communication. And then a client is talking to each of the servers. Well, if they get cut off from each other, the server that was isolated says, oh, I guess I need to recover this item and hand it off to one of my workers. And now both workers, they don't know any better. They're talking to RabbitMQ, and RabbitMQ's like, sure, you can have the lock. And now our lock is held twice at the same time. So we can prove this. Let's write a model. We'll say, here I'm going to define a new data structure called mutex. It's got a single field called locked. This is an immutable record. It's got a protocol that says, here's the functions you can call on this data type. And the function called step, that's our f function that determines the safety of the model. It's going to take a current record state R and an operation. We don't care about R. Then we'll dispatch, this is the cond, based on whether the operations function is equal to either acquire or release. If you're trying to acquire a record that's already held, you can't do it. That's inconsistent, so we say you can't do that. But if it's unlocked, it's OK. So you acquire the mutex, and we return a new mutex with state true. And vice versa for unlock. This is the whole encoding of a mutex, right? This is like the basic safety property. Does this make sense? Yeah? Cool. So this is all you've got to write to check something with Knossos. If you want a register, like your state is just the value of the variable, and your read's like, did I read the value that the variable contained? Right? You don't have to do any complicated multi-threaded concurrent stuff to check something. You just have to define the single-threaded model. And then Knossos does the rest. So it tells us that process 3 invoked an acquire operation on the lock. Process 2 invoked acquire. Process 2's acquire operation succeeded OK. And process 1 invoked acquire. But then something horrible happens. Process 1 acquire goes through OK. Well, hang on a second. Right? Let's try to figure out what the single-threaded history would be. It'd be like invoke acquire 1, and we'll release, and then we'll invoke acquire. Yeah, we've acquired. And now the current state is locked true. And then there's all these other processes trying to acquire the lock. But then one of those processes that's trying to acquire succeeds. It grabs the lock at the same time. And that leads to this inconsistent state transition. You can't go from locked to true and apply the lock because it's already held. So RabbitMQ is not a linearizable lock service. You're probably thinking this is not particularly interesting, right? Because it's still a perfectly fine queue. And in fact, we expect this because like exactly once delivering queues is impossible. You want to recover. You want to be non-linearizable. We do this for fault tolerance, because if a worker crashes, you need to recover your state somehow. Now, in my last talk, I said it's fine, as a queue at least. This was not entirely correct. RabbitMQ's documentation for clustering says that of the possible CAP theorem trade-offs, it chooses consistency and partition tolerance, or optionally consistency and availability, and we'll just ignore that and pretend it didn't happen. So the consistency and partition tolerance docs say the pause minority mode is the safest way to handle partitions. And in this mode, we'll shut down the nodes on one side, on the minority side. So you need to have a majority connected in order to keep running. So we'll expect that in a partition, on the majority side, those will keep handling requests. The minority nodes will shut down. Everything should be clean and safe. And in fact, we do see a shutdown. Like here, process 2501 has gone offline because it got a message saying the durable queue is down or inaccessible. And that's what you want. Right? Like, you should have unavailability for a consistent system. But it's not quite safe because it actually threw away, well, all of those numbers. Yeah, so that's almost 35% of acknowledged inserts into the queue were destroyed. This is a problem. So you can lose a lot of data. And this is not just a theoretical problem. I know of at least 2 production deployments of RabbitMQ that have seen this in prod. So the reason why this happens is because RabbitMQ recovers from a failure by nuking all the state on one of its neighbors. It just says whichever one is sort of authoritative as the home node, it's just going to replicate its state and clobber the other one. And if it clobbers one that has diverged somewhat, you can get into trouble. And how bad that trouble is depends on how long it's been diverging for. So if you shorten your timeouts, your divergence won't be as bad. So the Rabbit folks know about this, and they knew about it from the start, right? This is a design trade-off they made, and they're working to fix it. In the meantime, you can use the ignore partition mode, which will not shut down either side, so you get more divergence. But it also doesn't do automatic recovery. And so in that case, I think what you can do is dump both sides, merge them, and then re-enqueue them. But again, this is like a manual process, so it's kind of tricky. I also haven't tested this, so your mileage may vary. You obviously can't use the mutex. You've got a couple other options for distribution with Rabbit. You can use the shovel, which is a single point of failure, or you can use federation, which I don't really understand well enough. So open questions for future talks. Moving right along. we're totally over time. So etcd is a system based on Raft. It's a lot like Zookeeper. It's for configuration, coordination, consensus, offers reads, writes, value, and index-based CAS. So index is like update at this point in the history timeline. Now, the first thing I found is that there are lots of race conditions in this, which is a little interesting because I thought Go routines were supposed to make like concurrency a solved problem. Boo. I keyed. So the issue here is that it would actually hang the primary leader node when you did a join. And this is pretty reliable. Like basically 9 out of 10 times I tried to start the cluster, I was staggering it like 5 seconds, 10 seconds in between joins, and it would still like hang every time. So that was interesting. Blake Mizrani put a lot of work into cleaning up all that dynamic configuration code, and I think it's a lot better now. The etcd team was actually able to get the patches out in a matter of days, which is super awesome. You guys are responsive. I love that. And then I ran the tests, and the first thing I found was this like bad result. Not linearizable. Linearizable prefix, the portion of the history that's okay, was that process 2 invokes a compare and set from 1 to 4. Process 4 does a read, and that succeeds. And then process 2 changes 1 to 4. And then we've got this inconsistent op. Process 0 reads the value 1. Can you see the problem yet? Let's think. So Knossos will spit out these single-threaded histories that thought might have worked up until that point. So like write 1, read 1, read 1, read 1. So far, so good. Change 1 to 4, that's okay. That leads to the state 4. But then we read the value 1. You can't do that because you can't read 1 from a register that has a number 4 in it. It's just not okay. And the reason why this happens, well, you think about it graphically, right? Like we did this CAS operation and succeeded. And at this point, linearizability says you're not allowed to read anything from this past region. You can only see the value 4. But we didn't. We saw 1 instead. So that is odd because the whole point of Raft is to be linearizable, right? Like everything that goes in the log should have occurred in this sequence. But the reads don't go through the log. There are actually 2 classes of reads in etcd. There's a inconsistent read, the default, which just talks to any node and gives you basically any value from the past. And then there's a so-called consistent read, which actually just talks to whatever node thinks it's the leader right now and returns that. But Raft allows for multiple concurrent leaders. They're not necessarily the most up-to-date. And so you could actually do a read from a stale leader. So the top, we've got the new leader. It's taking the CAS from 1 to 4. That value is 4. Anybody that does a read against the new leader will see 4. Anybody that does a read against the old leader until it steps down will see 1. So I could read 1, then 4, then 1, then 4, then 1, then 4. I could get any sequence of reads out of this thing, and that violates linearizability. Also sequential consistency, because we could do 4, then 1, then 4. Also read your writes and monotonic reads, and this is bad. So this problem was sort of a fun one to find. And then the next day, HashiCorp released this project called Console. And they tested it with Jepsen, and they had this whole note about safety. And it's like, yes, this is great. I love testing. And they said, as a part of our console testing, we ran it against Jepsen to see if any consistency issues could be uncovered. During our testing, console gracefully recovered from partitions without introducing any consistency issues. This is not quite the whole truth. In fact, Jepsen did discover consistency issues. It discovered the same issue we just talked about in etcd. But what they did to fix it was to change the timeout for the leader from 1 second to 300 milliseconds, and then the test passed. So problem solved. And this is like really tempting, right? There's a whole number of like race conditions I've fixed by changing timeouts in a Java process. Many. So this is really satisfying in this sort of, no, it's not really satisfying. But it does work on the problem, it gets you to release, and that's important. And it shortens the window for inconsistency, which is also really good. But in a system that doesn't have real-time guarantees, i.e. anything running on the JVM or anything running in Go, which is garbage collected, or anything running on a Linux box, which is, of course, not like a real-time scheduler, or anything running on basically any cloud computer, you don't have these guarantees. Like it could just go to sleep and wake up some number of years later. So when this happens, you're going to have problems. This argument was successful, actually. Both Console and etcd were very responsive and agreed that this was an issue. They changed their documentation right away to talk about the fact that the reads were not linearizable. Yeah, right? This is good work. And they also have both introduced linearizable reads. So now the three classes of reads, the sort of weak read, the mostly consistent read that could occasionally be inconsistent, and then the actually linearizable read, which you pay a latency penalty for. So, like, great outcome. Good work, everyone. By contrast, Elasticsearch is a search engine. It's got a database inside of it, which does reads and writes, and you can do CAS against it. And then it's got this transaction log, which is replayed into a series of Lucene indexes, and you can do eventually consistent queries for search against those indices. When I evaluate a system for the first time, I go and look at the documentation. I try to figure out what are the guarantees, like how does it handle failure? And the thing that Elasticsearch, I mean pretty much all Elasticsearch says about failure is that it puts your data safety first. And that's really reassuring. I like that. And then my friend Bob over at Factual started showing me snippets from the Elasticsearch source code. This is actually not what you think it is. It's not quite that bad. But I mean, and again, like this is also in all of my software. Like, who among us is perfect? These are really hard problems, right? And we shouldn't fault people for occasionally taking shortcuts, but we should document those shortcuts. So I started looking a little deeper and trying to figure out what are the guarantees. And you can kind of infer from the fact that there's this MVCC model that there's some sort of atomic concurrent set that sort of implies linearizability. It's not spoken out loud, but the read constraints look like it. And there's also this single note about network partitions that say that index operations can only take place on a majority. So this kind of sounds like a CP system, but they won't come out and say it. So you go Googling for things like etcd, or sorry, like Elasticsearch network safety. And you get this post from 2010 by Shea Bannon, which says that when it comes to cap at a very high level, Elasticsearch gives up on partition tolerance. Stop saying this. Like, all right. So why? Well, I personally believe that within the same data center, network partitions very rarely happen. This is this is a belief, right? Like, and this belief may actually map to your data center. There are some data centers where partitions are really, really rare. You can spend a lot of money and put a lot of time and effort into redundancy, and you can get good guarantees out of your network. But what I'm interested in is what happens when your network is not great. So yeah, look for something newer, right? This is 2010. It was a simpler time. So there's this post from 2014 that says Elasticsearch gives up on partition tolerance. Ah, like, come on. And there's some stuff about availability which is wrong. Okay, to clarify, cap availability, every request has to succeed, right? So some people think that if a request returns an error, that is still available. It's not. Because you can always return error, like that's a sort of trivial case. So it looks like Elasticsearch is actually consistent, and so I start testing it, doing these compare and set operations and looking to see if they're linearizable. And the first thing I found is that the advertised instantaneous cluster transitions are actually closer to 1.5 minutes. This is not the end of the world, but lowering it makes the cluster unstable, and taking 1.5 minutes for every transition means that a test takes like 10 minutes to run, and that means it's sort of a slow process to iterate. The cluster status endpoint is of questionable veracity. It will happily return all green on every node, even when the cluster is wedged or hosed. There are also short windows of write loss during cluster transitions. Cool story. In this case, it lost writes number 176, 177, 178, and 250 and 251. Thank you, Vanna. Those writes were lost. But this is not super bad. Like, I can deal with very limited windows of update loss, maybe. But wait, there's more. Billy May is here with a database. I was pointed to this ticket in the Elasticsearch GitHub, and this is actually from quite a while ago, something like 2012. And it says basically that Elasticsearch has this assumption that network partitions are equivalence classes, that they cut things off completely. But certain partitions have nodes that bridge both sides, and in this case, you could see a majority of nodes from every node. So it's possible that you could have 2 concurrent primaries. Now, a real leader election system will not let this happen. But there's this thing called Zendisco, which is not a leader election system. It's the membership system inside of Elasticsearch, and it will allow for simultaneous primaries. Or more specifically, it tries not to, but it's not properly linked to the replication algorithm. One of the things I want to emphasize is that if you're designing a replication algorithm, it has to be coupled to leader state. You can't just assume like, oh, we've got one leader and therefore replication is safe. You actually have to thread all the operations through the state machine. Otherwise, there's some really subtle issues. And this is why Paxos and Raft are so complicated. So there's two primaries, and if this happens, this is the number of writes you lose. And there's not enough room on the slide. It goes on for several slides. But this is about like, lost track, 645 writes out of 1900. So that's not so great. But these are compare and sets, and that's okay, right? Because compare and set linearizability is hard. But there's an easier problem that Elasticsearch probably does right, and that's inserts. Right? So when you insert records, you give them unique IDs, and then you can have separate inserts on both sides of the partition. They're never going to conflict because they're unique identifiers, and you just merge them. So like, this is always something your database can do safely. Inserts never have to conflict if you use UIDs. Okay, they conflict. 688 insertions out of 2023 attempts that were successfully recorded were just like lost. So that's a thing. One of the interesting messages that came out of that particular test was document already exists exception, which is of particular interest because the docs say that the IDs are 22-character UUIDs. So what do they possibly conflict with? Like, what already exists? I don't. All right. So that was the ticket for intersecting partitions, and the Elasticsearch folks messaged me on Twitter and asked that I not pretend that I had proved anything or found anything new. So I like to report some new things. One of them is that Elasticsearch cannot handle total partitions either. It will happily lose, in this case, 17 writes out of 461. Again, these are inserts only. It's not CAS. So this is one of the easy problems that could be solved. That's a problem. Right? But we know that that's like handling total partitions is difficult because membership and latency and replication, they're hard algorithms, right? So let's try a single node because this is one that you can definitely handle, and the docs say that this works okay. It doesn't. Elasticsearch in this case lost 8 writes, so that's also a problem. Again, the numbers go down, right? So as your network partitions become less weird, the number of lost records goes down, and that's a sort of generally nice property. So if your network is less weird, you can expect less damage. And this one comes with some really interesting messages. My favorite is reason, do not exists as master, act as master failure. This is, I'm not sure what it means, but it's associated with a total like wedge cluster where the nodes will never recover. Like you can fiddle with the partitions and heal them and ask them to ping, and like they'll report green status, but they're just hosed. Like they won't even handle requests, and so you have to restart the nodes in the test to get it to work. This is actually sort of a common problem. We've seen this in production extensively. Even single node failures in Elasticsearch can cause data loss. Specifically, we have rebooted nodes and seen 1/8 of our data disappear. We have had rebalances for shards, which is a pretty common occurrence under write load, and that will cause continual data loss. In fact, at one point, we were losing data faster than we could replace it. This is not just us. And this is particularly interesting, right? Because like there's no acknowledgement of this on the website. There's no acknowledgement in the training. Like as far as I can tell, they just would prefer it didn't exist. And it's rare, right? Like there's lots of successful startups using Elasticsearch. Like it's not necessarily going to do this for you, but it could. And it does for a number of people. We've seen some bad networking issues, some SAN problems, VM stalls, 4 gigs of heap running on a 4 gig memory instance, which caused it to swap. Random GC spikes where a node is a member of both sides of the split. Frequently experiencing this mixed brain partition up to 3 or 4 times a week. Remember, network partitions are rare. I/O weight related, node A and node B cannot talk to each other, but they can both talk to C. So there's just a litany of these sorts of bugs. But there's good news, right? Which is that Elasticsearch has since closed the ticket. No, like they probably actually fixed it. I bet like it passed their test. They've put a lot of work into testing the distributed infrastructure. I know some people that have gotten Jepsen running, and this is a priority for them, right? However, this is not the end of the consistency issues. The problem goes much deeper. So the sort of latest news that I've got, and again, like I haven't updated the docs, right? Like if you're looking at Elasticsearch as an evaluator and you don't know about this stuff, it's gonna pretend to be okay. I would really like to see documentation that says, hey, if you see a partition, you could expect to lose data in this way. That would be a really great interim measure until you fix the problem. The way that they're fixing the problem is to address single node consistency first. So a lot of these partitions are caused by garbage collection, by I/O pauses, and in those cases, they think by improving the performance of a single node, you can do better. They don't want to adopt Zookeeper, which is actually kind of worrying for me because I'm not convinced that Zendisco is at all sound. In fact, I'm thinking Zendisco is terrible. There is a Zookeeper plugin for membership. It is not supported. It has been broken for several releases, but some people have tried to revive it, and they say it works, so that's worth trying. If you use Elasticsearch, you, I think, absolutely must store your data somewhere else. People say use Elasticsearch as a primary data store. I think that is crazy talk. Put your stuff in a real database, replicate continuously. We have these Bloom filter things that refill Elasticsearch every day. And that's OK, because typically you don't expect search to be fully consistent. So to sum up, I'm sure we're over time, but I'm actually just making sure you don't have a line for lunch. Jepsen tells you about one particular system. Again, lots of these databases work in production at dozens of companies. Elasticsearch has $107 million in venture funding, right? Plenty of people use it, plenty of people succeed with it. It can be really good software. It has an awesome API. This is not to say these systems are bad. They're trying really hard to solve really hard problems. That said, these failures are possible. If they're possible in your system is up to you. So I want to encourage you to ask questions like, what happens if my network partitions? What happens if I get partial partitions or one-way partitions? How do I rely on garbage collection pauses being low, because your process could GC for minutes? If VMware hops a VM from one place to another and your process, your OS pauses for 2 minutes, how is that going to affect your correctness? Ask yourself about clocks. Timestamps basically sync Cassandra correctness, and timeouts can sync the correctness of RabbitMQ and etcd for those reads. So understanding how you rely on timeouts and the exact guarantees your runtime offers is important. Ultimately, you also need to be aware that the clients are really part of the distributed system. It's not like the distributed system is this magical sky oracle. You actually talk to it and participate with it and have an active relationship with God. So the client state is really important, and it's easy to forget about that. Ultimately, I want you to reason carefully about the state transitions in your system that have the most critical impact. So oftentimes, only some things in your system are really important, and others can be discarded. And ask yourself about how much safety is really necessary. Banks, financial firms, people that do real business where the database ships $1,000 machines somewhere, oftentimes they find it's easier or safer to rely on apologies, to rely on insurance, to have customer support people call someone up and say, I'm sorry, we lost this. And then to do manual recovery from logs or to ask their customers to enter it again. That can actually be a more pragmatic outcome than having complete safety. And a lot of the time, your records aren't even that important. Look at Twitter DM. Twitter following relationships disappear all the time. Facebook messages come in out of order. Consistency is not required. And most of the time, the data that's really high volume or high throughput doesn't need to be that safe. And so you can have some parts of your system be really safe and very small, and other parts be very large and eventually consistent. Ultimately, you have to strike a balance between complexity and correctness in your system. And once you've struck that balance, you need to measure it to verify that it actually holds. So write a script to call your API, record a bunch of results, and then try to figure out if those results line up with your model of the system. And while you do this, kill nodes, use IP tables, drop a bunch of packets here and there. If you have a staging environment or a test bed, this is a great piece to have as a part of your CI. What I really want to emphasize, and what should be the takeaway, these particular bugs have been fixed or will be fixed, but what's more important is the culture that leads to the bugs, the culture that leads to errors. Database vendors have a vested interest in lying to us because it makes money, right? And a lot of times they don't have to want to. It's just that understanding consistency is hard, and the marketing people probably don't have that expertise or know how to communicate it, and the database people may not know how to communicate it. We're facing not just a technical problem, but a social problem. One that requires good writing, one that requires solid mathematics, one that requires empathy. So until this culture arises universally, I'm trying to push for people to evaluate their own systems, to check their own safety. This work could not have been completed without the help of many people. Shay Bennett from Elasticsearch, Cliff Moon, JD Maturin, Kobo Hale, Camille Fournier, and Jared Marl all listened to the talk. Ryan Zazeski, Blake Mizrani from etcd, Michael Klishnan and Alex P. from Langor, Evan Phoenix, Jeff Hodges, Shikar Boshan, Peter Bayless taught me everything I know about consistency models. Tyler Shewitt, Joseph Blomstead, Armand Dadgar, Zhang Li from etcd, Jacques Fuentes, Kelly Summers, Alvaro Data, who has a name I can't remember. It's like, something, he has a nom. Aaron France, and of course Comcast for funding this research, and Factual. Although this is a free time project on my nights and weekends, Factual has been incredibly supportive as an employer. Thank you all very much.